In this lecture, we're going to introduce multiplexers. We're going to talk about the notion of a tri-state. We're going to talk about decoders, encoders, and introduce adders. So up until this point, we've really been dealing with fairly low-level logic. AND gates, OR gates, NANDs, NORs, NOTs, those types of things. Now we're going to move up to a little bit more sophisticated level of logic, looking at those ANDs and ORs, NANDs and NOTs as building blocks for more sophisticated digital devices. And so we'll see how they can help us in a variety of ways to build up some digital functionality. So the first device I want to talk about is the multiplexer. A multiplexer is basically a digital switch that allows you to choose one of multiple inputs. In this case, this is the simplest multiplexer you'll ever experience, where you've got two different inputs over here on the left, and our select line A, or control input, allows us to choose. If A is 0, we're going to take the input I0 and put that out as the output over here on Z. If A is a 1, we're going to choose the input I1 and put that out there on Z. And so effectively A can be thought of as changing this switch, connecting it from I0 out to Z, or excuse me, from I1 out to Z. And the logic there is really what you see here. It's A prime, that would be when A is a 0 and I0 is a 1, that's when we're going to see Z go out to 1. Or if A is a 1, that's when we're selecting I1, and of course when I1 is a 1, that's when Z is going to go out to 1 as well. We can think about multiplexers basically being a data traffic cop. So at some point you might want your data to go in one direction, and at another point you might want data to come in from another source. So you can think about those data sources. One might be a north-south highway, the other might be an east-west highway. The multiplexer is deciding which highway has access, or which on-ramp has access to the road. And so you can think about that multiplexer as being like a data traffic cop. So multiplexers can of course be bigger than just a 2-to-1 multiplexer, as you just saw in the previous slide. You can have, for any number of select lines or control lines, you can have 2 to the n inputs. So if we add another control line, then we could have 4 different inputs. If we had 3 total control lines, then we can have 8 inputs, etc. And we can look at those using individual logic gates. We'll look at that in a slide in just a moment. So here are some different configurations. If you happen to have 2 control inputs, that'll allow us to select from these 4 lines. And the binary value for the input number would be what would determine which one of those inputs is ultimately going to go out on Z. So if you had, let's say A is your most significant bit and B is your least significant bit, then 0, 0 would allow you to select I0, 0, 1 would allow you to select I1, 1, 0, I2, and then 1, 1, I3. Excuse me. If you had 3 select lines here, 3 control lines, that would allow you to choose from 8. And in general, for any n control lines, you can have 2 to the n data lines coming in, and that will determine your output Z over here. We can represent this using the logic gates that we've seen previously. So in this case, this would happen to be a 3 select line multiplexer, 3 control lines. And you can see that in this case we would be selecting I0. So if you had 0, 0, 0 here for A, B, and C, and then you had a 1 for your I0, then that would flow on through. What you should notice is that each of these AND gates are mutually exclusive. Only one of those, at most, could be producing a 1 at any given time, and that's because there's only one of these where you would have a 1 on all 3 of these inputs at any given time, depending upon what A, B, and C happen to be. And then, of course, it depends upon whether you have a 1 or a 0 at that very moment on those input lines as to whether you get a 1 on out. So really we're just ANDing together all of the possible scenarios for what your select line is and the select situation in terms of A, B, and C, and then we're ORing things on the output. You can also cascade multiplexers. So if you happen to have multiple lines of data, let's suppose you wanted to send some data in parallel, so old parallel ports where you actually sent multiple data at the same time, you might just be choosing from 2 different data sources. And so one source might be X, the other source might be Y, and so you choose all the appropriate bits from X with one of the select inputs, or you choose all of the appropriate inputs for Y with the other. We can actually simplify that representation down to using a single multiplexer and then just putting this hash with the number of lines. So if you ever see some digital block diagrams, you might see hashes with the number of lines that are actually traveling there. That's just kind of engineer's shortcut so that you don't have to draw 4 different lines, or in this case 12 different lines, 4 for each of the wires that you see here. You can just say, well, there's going to be 4 lines representing X, there's going to be 4 lines representing Y, and our output here is going to be 4 lines on the output Z. Buffers are also quite important. These are particularly important if you have to send data over a long range, or if you have to send data to multiple different places. So what you can think about is the internet service providers in, let's say, a rural area. If they are trying to send internet data down to an area that may be a significant number of miles away from the home office or the source of the internet, then there may be some signal loss if that line has to go for a long period of time. Also, if you think about having, let's say, a high-rise complex that's very populated, and you're trying to send data to everybody in that complex, it could be internet data or phone data or all sorts of other things, then you might have a problem if you don't add a buffer. The buffer effectively is just like an inverter, except it just takes in and outputs exactly what it puts in. And that allows us to isolate this input logic from our output logic. You can think about this in terms of resistors. So every gate that you're putting on out here is basically another load, and you can think about that as a resistor load, and every time you add a resistor, that's going to change the amount of power that can be transferred out of those gates. So the buffer allows us effectively to isolate the input impedance from the output impedance, get a little bit better match, and a little bit more signal propagation on through without electrical loss. We introduced the notion of buffers there so that you could also understand the idea of a tri-state buffer. So in this case, we've largely, up to this point, really just thought about logic as being either 0 or 1. So if you have some digital device that is driving something, we've always thought, well, it has to drive it to a 0 or it has to drive it to a 1. In some cases, you may want to not necessarily connect that device all the time, or you may want it to not really have control over whatever it happens to be connected to at a certain moment in time. And so in that case, what you want to do is have a tri-state, or third state, which is Z, a high impedance, and what that will allow us to do is basically get that device out of the way so that the other devices can come on through. Well, when would you ever want to see that? Well, for instance, if you happen to have, let's say, 2 different sources driving the same actuator. So for example, let's suppose you had a stereo system, and you think about the modern stereo systems in vehicles, you've got multiple sources available. You might have an AM radio, you might have an FM radio, you might have a CD player, satellite radio, you could have an auxiliary jack, you could have music streamed over Bluetooth, all these different things. And you really only want to hear the music from one of those sources at any given time. So while your vehicle is perfectly capable of taking in the FM data, the AM data, the satellite data for satellite radio if you have that, perfectly capable of reading a CD if you got a CD loaded in the CD tray, you really only want to listen to one audio source at a time. And so all of your speakers happen to be connected to that same audio source. And if you're not using an audio source, you don't want it to control it. So your digital music might be represented as a series of 1s and 0s, but you don't want to send those 1s and 0s unless your device has control over the system. So if you were in a state where, let's say, you're listening to the satellite radio, then you want to basically cut off the ability of the FM radio to be able to send signals to the speaker system. So in that case, what you would want to do is establish a high impedance between the FM radio and the output speaker, so long as the FM radio is not the source that is selected. So in this case, we can represent that using a buffer like this, and that buffer has an extra select line B. And so if B happens to be a 1 in this case, then the input A will flow through to C. If B happens to be a 0, then there will basically be an open circuit or high impedance state between A and C. As you see illustrated right here, you can think about B as effectively opening and closing this switch. And so if it is open, that would be in the B equals 0 state over here, then whatever A is never flows on through to C. A only flows on through to C if B happens to be a 1, which would close that switch there. So why would we ever want to use it? Well, just as we were talking about, what we want to make sure is that we don't have a logical contradiction. So a lot of times modern digital systems use a bus. And what a bus is, it's not a vehicle that is used to go to school or around public transportation areas. But what a bus is in a digital system is really just a shared highway where data can run on. And that shared highway has to have some rules that govern who can have access at any given time. So if you happen to share a data highway amongst various devices, you want to make sure that devices that should not have access to the highway right now basically just get on out of the way. And so the tri-state, having that third state, the high impedance state, allows those devices that should not have access to that highway right now to get on out of the way. There's multiple ways that we can represent tri-state using buffers or inverters. This is what we just saw here. So if we look at the truth table there, if B happens to be a 0, what you're going to get out is high impedance. That's the Z value here. And it does not matter what A is in those cases. So you can basically think of, if B is 0, then A is a don't care. If B is a 1, then whatever A is happens to be what comes on to the output. This is exactly the same thing, except now you have this bubble out here, so your C output when B is activated is going to be the inverse of A. So that's what you have here. If you have B activated, then A, when it's a 0, produces a C that is a 1. When it's a 1, produces a 0, vice versa. And of course, when B is a 0, you still get this high impedance or Z state there. These happen to be the exact same thing, except notice where the bubble is now. This bubble says that this is active when B is a logic 0. So in this case, we've reversed the logic of this buffer and said this buffer is going to be active when B goes low. So in this case, when B is a 0, this is just a regular buffer. A flows on straight out to C. Same idea here, except now we're back to an inverter. And so when B is a 0, the inverse of A flows on out to C. You can actually establish a multiplexer using these tri-state buffers. So if we happen to have this simple 2-to-1 multiplexer where B is our control line, notice what happens here. If B is a 1, which of these buffers are we going to activate? This one down here at the bottom. So when B is a 1, C is going to be able to flow through to D. When B is a 0, you're going to activate A, which will flow on through to D. And notice that those are mutually exclusive. So you'll never have to worry about data conflicts on your D, because you can only choose one or the other of these buffers to be activated at any given time. A decoder is another device that you should be very familiar with. It allows for inputs to basically be translated from binary into activating a single line output. So if you happen to have 0, 0, 0 for your A, B, and C, what you're going to do is activate Y0. So that would put a logic 1 on your Y0. If you happen to put in binary for, let's say, 4, 1, 0, 0, then what you would do is activate Y4. And so here's the truth table for that. At any given moment, only one of the outputs is activated, and all the rest are logic 0. You can also have inverted decoders, and so in this case we're going to have 4-bit input and we've got 10-bit output, but notice these bubbles, they indicate that the logic coming out is the exact opposite of what we had in the previous example. So in this case, you're going to have 1s on all of your outputs except for 1, and that 1 is going to be where you have the logic 0. So if you happen to look at the truth table for this device, this is what it looks like here. So notice you only have the single 0 if we are within range. So this particular example, there's no outputs for 10 through 15. You can think about this as a binary coded decimal. inputs. So in this case, we're just going to be able to represent the digits 0 through 9. Here we are using a 4 to 10 line decoder to actually realize a minterm expansion. So if you happen to look at this equation here, M1 or M2 or M4, you could actually write that like you see down here. We can just use De Morgan's law and rewrite that as M1 prime, M2 prime, M4 prime, that whole quantity primed. And so in that particular case, what you can do, you notice that this happens to be the complement of all of those, and it together and then primed. When you AND something together and prime it, that's basically using a NAND. So what you can do, if you have your minterm expansion, is just have a NAND gate that pulls from an inverted decoder all of the minterms that are involved there. And you can use these NAND gates to realize F1. Very similarly, you can also realize F2. Encoders are the exact opposite of decoders. So in this case, you can activate one line and it's going to figure out what the binary representation of that is. In this case, we've got an 8 to 3 priority encoder, and priority encoder really just is talking about the order of operations, or the order that you select different lines, because what this is doing is it's giving priority to the higher order inputs Y. So if Y7 happens to be activated, then, meaning has a logic 1 on it, then it does not matter what any Y0 through Y6 is. And that's what you're seeing in this last row. If you have Y7 activated, then your output then and only then will be 1, 1, 1. If you happen to have, let's say, Y4 activated, then if that's the first of the higher priority inputs that are activated, then your output will be 1, 0, 0 for a binary for 4. But in this case, we always look, there could be multiple lines activated, but we always look for whatever the highest numbered value, or highest numbered line happens to be. So in this case, that's why we have these don't cares. So if you have, for instance, Y7, we don't care if Y2 or Y1 happens to be activated. The highest number input is that Y7, and we will ignore the rest. In this case, what you get out on A, B, and C are the binary for the line number that is activated, the highest number line number that is activated. And over here, this D is just used to indicate that you do have some data. So the only way that that goes to 0 is if you don't have a 1 on any of the input lines, Y0 through Y7. Otherwise, you're going to get a 1 on D when you have any of those inputs activated. Adders are very important to digital logic devices. You can think a lot of times you want to be able to do simple arithmetic, and adders are very important to be able to do that. So let's think about how you would go about adding two 1-bit values together. So we'll start with the simplest possible binary example, and then we're gradually going to build it up to a more and more complicated example. So if we think about adding just two 1-bit numbers, let's say we have the 1-bit number A and the 1-bit number B, as you see here. The possible range of values, A can go 0 to 1, B can go 0 to 1, so therefore the sum can be either 0, 1, or 2, depending upon the values of A and B. So in this case, we see the exact truth table there, and we could start to realize this using logic gates, but before we do, we probably want to think a little bit more in terms of how we're going to represent that output. Well, in this particular case, since we need 2 bits, because we can get a sum of 1, 0, or 2, then we need to make sure we have 2 different binary outputs. And in this case, we can just label them as X and Y, as you see on the truth table over here. So given inputs A and B, which we will treat discretely, then you might get outputs X and Y, as you see here. So let's expand this. That was a very simple example, just involving two 1-bit values. Let's suppose we made our values a little bit bigger. So let's now suppose we wanted to do two 2-bit values added together. So each of those values could take on the range 0, 1, 2, and also 3. So the sum could be between 0 and 3 plus 3, or 6. So how many inputs would we need? Well, in this case, we're adding two 2-bit values, so we need 4 inputs. How many outputs would we need? Now keep in mind that our sum is going to range between 0 and 6. So you need to think about how many binary digits it would take, or binary places it would take for you to represent that sum. And hopefully you figured out that that happens to be 3 bits, because to represent 6 requires up to 3 bits. Then the question is this function incompletely specified? That is, for all possible input values, is there a corresponding output value? And in this case there is. However, there is a little bit of a caveat in that the possible output values do not span the entire range from 0 all the way up through the maximum possible value that can be represented there. So for example, when you're doing 2-bit input, you cannot get a sum of 7. So if you were to add the maximum possible value from the first input, maximum possible value from the second input, you could not get a total anything greater than 6. So the function's not incompletely specified. However, if you were to use the output from that addition to drive another circuit, then that other circuit would be incompletely specified, because it's not possible to achieve that particular set of input combinations for the next stage. So here's our block diagram for the 2-bit adder. In this case, N1 and N2 are our two numbers that we're adding together. And then our summation comes over here at N3 on the right-hand side. So you can see, just for adding 2-bit values, we're starting to get a little bit more complicated. And here would happen to be the truth table. So remember the truth table that we went through for the 1-bit arithmetic. Now let's think about that now that we happen to have 2-bit arithmetic. And so here we go with our 2-bit arithmetic. Because we now have 4 inputs, that means we have to have 16 rows in our truth table. And so things have gotten a little bit more expanded since our single 1-bit example. This would be a 4-bit adder. So if you had 4 different bits of A added to 4 different bits of B, we can also add in a carry in. So that would be our C0, and a carry out, which would be C4. So that would allow us to actually cascade these together to where you could have, let's say, instead of just a 4-bit adder, you could have an 8-bit adder and just carry the carry out, C4, into the carry in for the next stage. So this requires 9 inputs, 4 each for A and B, and then 1 for the carry in. And it requires 5 outputs, the summation bits for 4, and then also the overall carry out, if there's a carry out from that sum. So in general, n-bit adders, every time we add another bit to one of the add-ins, we really double the size of our truth table. And if we add one of those bits to both add-ins, then we're actually quadrupling the size of our truth table in terms of the number of rows. So you saw that we went from just single bit to 2-bit. You can imagine how big that truth table would be if you happen to have larger values. In reality, that's not exactly how we implement these things. Really what we do is look at the individual summation that happens 1 bit at a time, and we consider whether there was a carry in. We consider what the summation would happen to be in terms of going and writing that down below the line if you were to write out 2 binary values to add together. And we also consider whether there's a carry out to the next digit. So one thing to note, that is called a full adder. If you hear anyone refer to a half adder, that's where you have no carry in input. So the half adder only considers the 2-bit addition without any carry. So here is how that might work. So you would have, for a full adder, an input A and an input B, 2 1-bit values. You'd have a carry in, and then you have to output the summation and output the carry out. And so that's really just based on if you write out 2 binary values and start adding them together and thinking about what happens. If you have a sum in those 2 bits and the carry of 0, then your sum output would be 0, your carry would be 0. If you add those values together and you get a sum of 1, then your sum bit would go to 1 and you would still have no carry. If you added those together and you got a 2, well, we can't just write down 2 as our output. That has to be binary. So we would have a carry out of 1. Oop, let me go back. A carry out of 1 and a sum of 0. And then the largest you could possibly have is a 3. That's the case where you had a carry in and then both of the values being added together are 1s. In that particular case, your sum bit would be a 1 and your carry bit would be a 1. So here is our truth table for the full adder. Let's think about what's happening if x and y are the 1-bit values we're adding together, and then cin is the carry in coming in. So if you happen to have 0, 0, 0, then what you might have for your output would be a carry out of 0 and a sum of 0. If you happen to have a value of 0, 0, 1, then the sum there would be 1, so you would get a 1 and a carry out of 0. Similarly, 0, 1, 0, it doesn't matter what order these numbers come in. If you have that, your sum is a 1 and your carry is a 0. If you have a 0, 1, 1, that gives you a sum of 2, but we don't write that as 2. We write down our sum as 0 with a carry out of 1. And here again, 1, 0, 0 is a sum of 1. Here again, 101 happens to be a sum of 2, so that puts us as a carry out of 1 and a sum of 0. 110, same thing, happens to be 2, so a carry out of 1 and a sum of 0. And then 111 gives us a sum of 3, so there we have a carry out of 1 and also a sum of 1. So that is the truth table for the full adder. You could go through the basic logic structures that you worked through before to develop combinational logic, but we can represent these using this logic here. What you'll actually notice is that the sum can be made using an exclusive OR gate. What an exclusive OR gate does when you have more than 2 inputs is it effectively acts like an odd detector. So if you happen to have an odd number of bits, whether that happen to be 3 or 1, that's when you're going to get a 1 out. When you happen to have an even number of bits, whether that's all zeros or 2 1s or something like that, when you have an even number of 1s, then that is when you're going to have a 0 output there. So your sum can be made using a 3-bit exclusive OR gate, and then your carry out comes from this logic here. And that generally happens whenever you have anything where you have 2 1s. So if x and y were both 1s, or x and carry in were both 1s, or you had y and a carry in any of those cases, you would have a carry out. We can also use an adder as a subtractor, and this goes back to how we formulated 2's complement numbers. So if you remember how we made the 2's complement, what we did was we flipped all the bits, or inverted all the bits, to make the 1's complement, and then we added 1. So that's how you can start with an unsigned binary value and make the negation of it. And really, subtraction is just adding the negative of a value. So if you can form the negation of a value as one of your summation, or one of your add-ins in a summation, then what you can do is subtract. And so we can do that using some of the gates that you've already seen. So you can use NOT gates to flip all those bits, effectively formulating the 1's complement. And then you can add in a 1 on your carry in, which would allow you to have that plus 1, making it the 2's complement. So here's what that would look like. If we're trying to develop something that would be A minus B, then our B, we're going to invert all the bits, so we have the 1's complement of B, and then we're going to have a carry in of 1, which effectively gives us the 2's complement of B. So that's what we happen to have there, and then the summation happens exactly the same way. Alright, so this concludes our lecture here. I hope you have enjoyed learning about these different devices.